And what I would encourage you to do, instead of plugging the numbers in and rearranging, go ahead and take the range equation and simply solve it for v. You multiply by g times x range equals VO squared sine of 2 theta. I divide by sine of 2 theta and I get x, so g x range divided by sine of 2 theta equals VO squared. So to get VO, I simply take the square root of this. Okay? And I'm not going to plug the numbers in, but you simply use this equation, you plug in the range of 31 feet, and you plug it in the angle of 35 degrees, and what should pop out from this equation is the initial velocity. So that's question, that's number 6. Okay, question number 7. Okay. A football kicker is kicking off. He wants the ball to have a range of 67 yards or 195 feet so that it will land on the end zone. If a kicker can kick with a speed of 81 feet, what is the angle? Well, this is just like the same kind of a question. We know that the initial velocity is 81 feet per second. We know that the x range is 195 feet. The question is, what is the angle? The angle is equal to what? Well, this is just really the range equation where we solve for the angle. Now we take that equation and we solve it for this angle. So we simply rearrange it. Whoops. We say G times X range divided by VO squared equals sine of 2 theta. Okay. So in this case, I'm gonna go ahead and plug in the numbers here. Okay, so this would be 32 feet per second squared times 195 feet divided by 81 feet per second square, feet per second, and I square that, and I get, let's see, 32 times 195 divided by 81 squared, and I get 0.951. That's equal to the sine of 2 theta. So what do we do now? What we do is we take the inverse sine. Basically 2 theta now is equal to the inverse sine of 0.951. Okay? So this means that 2 theta, I'm going to write it up here, 2 theta equals the inverse sine, whoops, the inverse sine of 0.951. So 2 theta, if you take 0.951, do arc sine or inverse sine, I get 72 degrees. Okay, so that means theta is equal to 72 degrees divided by 2, which is 36. 36 degrees. So the angle should be 36 degrees. Okay? All right. Number Number 8. Number 8, a golfer hits a ball up to the green, which is on the top of a hill. Now this problem is a little bit trickier. If the ball's initial velocity, here's what's happening. It's something like this. Can you see this? Yes. The initial velocity, the ball is coming up with this initial velocity of 75 feet per second. And this angle here, the angle is 60.0 degrees. Now what happens is the ball comes up and bam. It's not allowed, because of the hill, the ball is not allowed to fall all the way down. Now if the hill is not here, it would fall, let's say, and hit here, but the hill is here, and so it collides right here. So the question is, let's see, if the ball's initial velocity is it hits the green at 94 feet. So this distance from here to here, this x distance, is 94 feet. And the question is, how high is the hill? Okay, how high is this from here to here? Okay, how high is it? Now this is a little bit trickier problem because we're not at the peak and we're not down here at the ground level. We know how to solve those problems because if the golf ball came all the way back down to here, it would be the range equation. If we're at the peak, then we could solve like for taking the y dimension and solving for where the y velocity equals 0. But in this case, we can't do that because we're not sure. We don't know if it's before the peak or after the peak, or we don't know anything about it. The only thing we do know is what this is. Okay? So, how do we solve this? Okay. Well, what we do know is, we do know what the distance is. Now notice, fortunately they gave us this. Because we know this, remember that the horizontal distance is the velocity in the x dimension times the time. We know what this is. We know there's 94 feet. We know what the horizontal velocity is, or we can calculate that. The horizontal velocity is simply the initial velocity times the cosine of the angle. We know we can get that, so therefore we can solve for the time. Once we solve for the time, then we can use in the y dimension the equation well, this should be a minus. In the y dimension, we can use this equation. We solve for time. We take using this equation, which is in the y dimension. Notice y equals the initial velocity times time minus 1/2 plus 1/2 at squared, where a is minus g. We solve that. We know what the initial velocity is in the y dimension. We solve for t, and we can find out what the h, or this distance, horizontal vertical distance, is. Okay, so here's our two-step process of how we're going to do it. Let's solve for t here. The x distance is the horizontal velocity, is the initial velocity times the cosine of the angle times t. So t here is x divided by that's t. So we can solve for that. So t is 94 feet divided by 75 feet per second times the cosine of 60 degrees. Okay, so let me take out my calculator here, and I say 94 divided by 75 divided by 60, the cosine of 60, and I get that it's 2.5, we'll round it off to two significant figures, 2.5 seconds. Okay, so it's 2.5 seconds. Now we can take so that's how we solve for time. We can now take this, the 2.5 seconds here. So t is 2.5 seconds until it hits this. We can now plug this into here, and we get h equals the initial velocity in the y dimension, which is the initial velocity in the y dimension is VO times the sine of 60 degrees. So we have 75 feet per second times sine of 60 degrees times 2.5 seconds. And we have to subtract now 1/2. G is, in English units, is 32 feet per second squared times 2.5 seconds squared. And we end up with, so there's two terms. The first term, 75 times sine of 60 times 2.5, we get 162.4, and I'm going to worry about the significant figures soon. They're going to calculate this. 2.5 squared times 32 times 0.5, and I subtract 100, so I get 62, rounded off to two significant figures, feet. So h here is 62 feet. And I hope that you have, I hope that makes sense, that we broke it up. First we had this, we used the horizontal distance here to solve for the time. Then once we had the time, we use this equation to solve for the exact y. That's a little bit of a more of a kind of a trickier problem, because the problem does not involve solving something right at the peak. When you solve for something that's not exactly at the, it's not at the peak, nor is it not over here, the only way to really do it is to solve, somehow you have to solve for the time and plug the time into this equation, the y dimension equation. Okay, that was number 8. Now on to number 9. Okay, a pitcher throws a baseball horizontally at a wall that is 51 feet away. So the ball is going horizontally. If the ball, he throws it, and the ball, of course, falls a little bit. If the ball falls 2.9 feet down, what is the initial velocity? And this distance here, what's the distance? This distance is x is 51 feet away. So here's the situation. Someone throws a ball horizontal, 51 feet away. He aims it right, perfectly horizontal at the wall, but it in fact falls 2.5 feet down. It's 51 feet away. Can you use that to determine the initial velocity? Yes, you can. Okay. What's the very first thing we need to do is to look in the y dimension, and we have that the y equals the initial velocity in the y component times time minus 1/2 at squared, or gt squared. The acceleration here is minus g. The initial velocity in the y component is 0. So the initial velocity in the y component is 0, okay, initially. So this says this, so here, this will be our y. Our y in this case is negative h. Notice that the y here is 0, and we're going down negative h to get to here. So we have negative h, and h, by the way, h is our 2.9 feet, equals minus 1/2 gt squared. So we can solve for the time. Minuses cancel out, and we get 2h, 2h divided by g equals t squared. So t equals 2h divided by g. So we can solve for that, and we get 2 times h is 2.9 feet divided by 32 feet per second squared. Take the square root of that. Notice that the feet cancel out, and 1 over 1 over second squared is second squared. Take the square root of that, that's seconds. 2 times 2.9 divided by 32, and take the square root of that, and so I get t is 0.43 seconds. Okay, now that we know the time, we can use the horizontal dimension, to say that the x distance is the horizontal velocity times the time. We take the time and plug it right in here, and so we can solve for the velocity. So the velocity, the horizontal velocity, is the distance divided by the time. So we have 51 feet divided by 0.43 seconds. Therefore, the initial velocity must be 51 feet divided by 0.43, and we get 118.6. We must round it off to 120, or 1.2 times 10 to the second feet per second. Basically, it's 120, but to show the two significant figures, we would say 1.2 times 10 to the second feet per second. So that would be the velocity of the baseball. Okay. Now on to the last problem, number 10. Okay, number 10. A little boy is playing with a toy car, and it rolls across the table 4.1 feet high, and it gives the initial speed, and it rolls off the edge onto the floor. So it's kind of like this. Here's the table, and here's the car, and it zooms off with an initial velocity of 1.2 feet per second. And it goes bang, it hits right there, and it's horizontal, and this distance from here to here has a height of 4.1 feet. Okay. The question is, how far away from the table will it land? So what is this distance from here to here? From the table, edge of the table, to where it hits the ground. What is that distance? Okay, this is similar to the other situation where we first have to solve for the time. Remember, this is just like the situation where if I hold up this car or ball from the exact same height and drop it, the time it takes to reach the ground is the exact time it takes this car to reach the ground. The initial velocity here, the initial velocity in the y is 0. There is no initial velocity, just like the initial velocity in the y direction here is 0. So gravity just pulls it down. So these two, the ball that I just dropped and the car, will hit the ground at the same time. So therefore, we can say that in the y dimension, the y is the initial velocity in the y dimension, which is 0. There is no initial velocity, minus 1/2 gt squared. So we can solve for t. So this distance, this is h. Or actually, it's because our datum is y equals 0 right here. This distance down is minus h. So I have minus h equals minus 1/2 gt squared. The minuses cancel out again, and we have 2h over g equals t squared, or t equals 2h over g. Okay, we can plug in these numbers. I'm going to put it over here. T equals 2 times 4.1 feet divided by 32 feet per second squared, and square root of, and I get 2 times 4.1 divided by 32 square root of, I get 0.51 seconds. Okay, 0.51 seconds. So therefore, in the horizontal dimension, in the x direction, we know that the distance traveled, is the horizontal velocity times time. We know what the time is, so we can say that the x over the t is the horizontal velocity. That's what the horizontal velocity, we're solving for t, solving for x. I thought we were solving for velocity, oops. So, here we go. We plug in what the initial velocity is. It's 1.2 feet per second, and we multiply that by 0.51 seconds. The seconds cancel out, and we get that this distance is, sorry things are squished here, this distance is 1.2 times 0.51, it's 0.61 feet. Okay? So again, to solve this problem, you use the y component to figure out the time, and you use a horizontal component to solve for the horizontal distance. Well, this concludes all the problems. And I hope this gives you a good understanding of how to solve these two-dimensional motion problems. We'll talk with you later. Bye. Hello, this is Module 4, the overview to the lab. Actually, there's two labs we're going to go over. The first one is it's the lab for Module 4, projectile motion. Now there's actually 3 parts to this lab. The first part of this lab is where you're going to take, let me see this. The first 2 parts of this lab is where you will use a little projectile launcher, something like this. You put, the gun will either look something like this or a little bit different depending on the type of gun. But in any case, you put the projectile in here, pull the trigger, whoops, it went off prematurely. I have another one. So, I load it, and then I launch the gun. What I'll do is I will set the gun at whatever orientation I need to set it off, and I use my meter stick. For instance, in the first part in part A of the lab, we have a table, and we set the gun right flat on the table, and we shoot it horizontally. It's horizontal, and it flies out here, and then we measure the distance exactly from where this is, exactly to where it hits. Okay, now how do we measure where it hits? We have to spot it. So we set the table, we get a table, we have to measure this height exactly to the center. When we measure it, we measure as accurately as you can in centimeters from the floor up to the center of the little missile, the little plastic projectile. We measure that in centimeters. It might be like 78.32 centimeters as an example. And then somebody fires it while another person observes where it hits. There's going to be a little bit of uncertainty here, so maybe you measure it, and actually, oh, you know what? I said measure this in centimeters. Actually, we're going to be measuring this in inches. Because this may be a long distance, use a tape measure where you can measure it in so many, let's see, we're going to measure this in inches. So maybe this will be 56.4 inches, and this may be 112.3 inches as an example. So we lay it horizontal, and then we shoot it. Whoops. And someone's over there measuring where it lands on the floor. Now, because there's going to be error in this, and error of judging exactly where this thing hits, and the fact that these are spring-loaded little guns here, and they may not fire exactly the same velocity every time. If you look on the lab, we're going to do 10 repetitions. So we shoot this 10 times, we spot where it lands 10 times, and then we take the average of all of those measurements. We take the average of this. And if you look on page 1 of the lab, it goes through the derivation. I'm not going to go through it now, but it goes through the derivation of the initial velocity. Basically, we can calculate what the initial velocity is. The initial velocity is this distance that we measure divided by the square root of 2 times h all divided by g, where this is h. And on page 2, we take our data, we're going to do 10 repetitions. This becomes the average. This is the average of 10. So we're going to calculate what the average velocity coming out of the gun was. The table is set up so you can easily calculate the standard deviation. What I want you to do is to calculate the standard deviation of this too. And then one of the questions is to then calculate if I have a standard deviation, if I have a delta x standard deviation, what does that correspond to the velocity standard deviation? There's a question about that. I want you to answer that. Okay, so that there's 5 questions in all on part A. Okay, in part B is a little bit different. In part B, we're actually doing a full projectile motion across the floor, where we're putting, this is part B, where we're laying the gun at a certain angle. And this angle here is critical, and we're going to measure